area between curves. In this section, we're going to develop how to determine the area of a region between curves using calculus. In Calculus 1, we learned that the area under a curve could be represented by a definite integral. And so a quick reminder of that idea was if we had this region under a curve from a to b, under the curve f of x on the interval a to b, the idea was we drew a representative rectangle and we said that it had thickness delta x, and we chose a sample point in some interval. We called that sample point xi. And we said that the delta x could be thought of as b minus a divided by n, where n was the number of partitions that we were going to use. And what we said was, okay, if I can find the area of that rectangle, well, the area of a rectangle is easy, right? All I would do is take the function at that x sub I, and I would multiply it by the delta x. That's the area of one rectangle. And then what we said was, okay, if I add up a bunch of rectangles, I equals 1 to n, where n was some, number, then this would give me a good approximation of that area. And then we went a step further. We said, well, if I take the limit as n approaches infinity of that expression, if I added up an infinite number of little rectangles, then as n approached infinity, this became what we called the integral from a to b of the function. And then we had that differential operator, that dx. And so this was how we could find the area under a curve. We integrate the function from a to b, and that gives us the area. So now, if we wanted to find the area between curves, well, we can use the same basic idea. If I draw a representative rectangle, there's my rectangle. I can still think of there being a delta x. I can still think of there being, this x sub I. I can still calculate the area of that rectangle. But now the area of the rectangle would be not just, I couldn't just think of the f of x evaluated at the x sub I. Now I've got to find that difference. So the area of the rectangle is going to be f of x sub I minus g of x sub I, but still times the delta x. And then, like before, if I let the limit go to infinity, right, if I add up a whole bunch of little rectangles, then this area, right, that area I'll call S, is equal to the integral from a to b of f of x minus g of x dx, as long as the f of x is greater than or equal to g of x over the interval. And so this is how we can find the area between curves. We take the integral from the lower limit to the upper limit of the upper function minus the lower function, and then with respect to the variable. All right, so here's a good introductory example. Determine the area bounded by y equals x and y equals x squared. All right, well, hey, they didn't give me a lower limit and an upper limit. Oh, let's draw it. Let's see what happens if we draw it. All right, so axes, y equals x, hey, that's just the line. Y equals x squared, hey, that's a parabola. So I'm talking about this region right here. What's that area right there? All right, so that's my S. All right, now I need to figure out the lower and the upper. I need to figure out what's the A and what's the B. And so to do that, what I'm going to do is I'm going to solve the system of equations y equals x and y equals x squared. All right, so I'm going to use a little substitution. If y equals x and y equals x squared, then x is equal to x squared. And so then 0 is equal to x squared minus x. 0 is equal to x by x minus 1. And so x equals 0 or x equals 1. So A is 0, B is 1. Over that interval, the upper function is x and the lower function is x squared, right? This is y equals x and this is y equals x squared. And so what I can do to find this area, and I've called it S, so this area S would be the integral from 0 to 1 of x minus x squared dx. All right, we can calculate the antiderivative. That's 1/2 x minus 1/3 x cubed. I'm sorry, 1/2 x squared minus 1/3 x cubed, and evaluating over 0 to 1. And so that would be, let's see, I'd have 1/2 by 1 squared, that's 1/2 by 1, minus 1/3 by 1 cubed, so again that's a 1, minus 0 minus 0. So it's a half minus 1/3, 1/6. That area bounded by those two curves is 1/6. Determine the area bounded by y equals x cubed minus x and y equals 8x. All right, let's see. I want to draw this. Drawing always helps. Y equals 8x, that's a line with a slope of 8. Y equals x cubed minus x. Let's just do some basic analysis here. That's x by x squared minus 1. That's x by x minus 1 by x plus 1. All right, so it's a cubic polynomial. And with the lead coefficient positive, it starts in the lower left and ends in the upper right. It has 3 x-intercepts at -1, +1, and 0. All right, let's see what we have here then. All right, so drawing this. -1, +1. And I know, since it's a cubic polynomial, it's going to do something like this. And then y equals 8x, that's just a line with slope 8. So I'm just going to draw a line with a positive slope. That looks like that. All right, we need to find some points of intersection. 0, obvious, right? 0 appears to be obvious, but the other ones are not as obvious. So let's solve the system of equations. Where's x cubed minus x equal to 8x? Let me subtract the 8x from both sides. X cubed minus 9x equals 0. So that's x by x squared minus 9. So that's x by x plus 3 by x minus 3. All right, so that tells me that we have intersections at 0 -3, and +3. All right, so then I'm going to think of this region right here. I'm going to call this region S1, and I'm going to call this region here S2. And so my basic idea then would that the total area I'm calling S would be S1 plus S2. Now let's see, S1 would go from -3 to 0. The upper function is the x cubed minus x. The lower function is 8x. And I would have to integrate that with respect to x. Then S2 would be from 0 to 3. And over 0 to 3, the upper function is 8x, and the lower function is x cubed minus x. And again, with respect to x. And we can calculate each of these integrals. We have the tools for that. I'm not going to bore you with those details. You can do those. But this first integral ends up being 20.25. And the second integral, the integral from 0 to 3, is also 20.25. And I guess, that might surprise you, but if we look at this graph and we think, hey, both of those are odd functions, it seems reasonable that there's a bit of symmetry between the curves. And so then the total area is 40.5. The graphs of y equals sine x and y equals sine 2x intersect infinitely many times, forming an infinite number of repeated enclosed regions. Find the areas of these regions. All right, let's see. I'm going to draw it first. All right, so y equals sine x and y equals sine of 2x. I remember the basic shape for sine x. I know that sine x has period of 2 pi. Let me graph this in blue. Y equals sine x is in blue. And I know its amplitude is 1. Period is 2 pi. And so I'm just sort of forming some points here. So I know the halfway, I know it starts at a 0. It ends at a 0. The halfway point is a 0. And I know it increases to 1 before it begins to decrease. So y equals sine x looks like this. There's y equals sine x. Now y equals sine 2x, remember that that 2 adjusts the period of the function, and the period then would be 2 pi over 2, the period is pi. So it's the same basic shape, but it's repeating the cycle in half as much time. And so y equals sine 2x is going to do this. And so what we have is these repeat, and I only drew it over 0 to 2 pi, but this same thing's going to repeat over and over and over again. And so I'm going to think, okay, here's some regions. I'm going to call this S1. I'm going to call this region S2, S3, and here's S4. Now, to calculate these points of intersection, to calculate these areas, I've got to find the points of intersection. So I need to know where is sine x equal to sine of 2x. I recall a property, an identity from trigonometry that says that sine of 2x is the same as 2 sine x cosine x. And I'm going to solve this equation like it's a polynomial equation. So then 0 is equal to 2 sine x cosine x minus sine x. Factoring. 0 equals sine x by 2 cosine x minus 1. So then sine x equals 0, which implies that x equals 0, pi, 2 pi, etc. And setting 2 cosine x minus 1 equal to 0, then cosine x would equal 1/2. And if cosine x is 1/2, that implies that x is, let's see, pi over 3 and 5 pi over 3, if we're just looking over 0 to 2 pi. All right, so let's see, what's the area of S1? Well, S1 would be the integral from 0 to pi over 3. And over that interval, let's see, we would have sine 2x minus sine x. I would have to integrate that with respect to x. Now, on this one, you're going to have to use a little bit of a substitution here. So let's do this one out first. Integrating sine 2x, remember that the antiderivative of sine is negative cosine, but since it's a 2x, we would have to have a 1/2. So I would have negative 1/2 cosine 2x, and then the antiderivative of negative sine x would be plus cosine x, and we'd have that over 0 to pi over 3. All right, so then substituting, let's see, I would have then negative 1/2 cosine of 2 times pi over 3. The cosine of 2 pi over 3 is a negative 1/2, plus the cosine of pi over 3 is positive 1/2, minus, substituting zeros. The cosine of 0 is 1, so I'd have a negative 1/2 plus 1/2. Cosine of 0 is 1. We go through all this arithmetic. Let's see, I'd have 1/4 plus 1/2, that's 3/4, minus negative 1/2 plus 1 minus 1/2, and so that's 1/4. So that's S1. S2. That would be the integral from pi over 3 to pi, and over that interval the upper function is sine x, and the lower function is sine 2x. Again, dx. I'm not going to go through all the steps here. The antiderivatives are the same. The order's a little bit different. The evaluation is a little messy, but if you go through all this, you're going to get 9/4. S3. Well, that would be the integral from pi to 5 pi over 3. And notice again, the order, the upper function is the sine 2x. And the lower function is the sine x. Again, with respect to x. And if you go through all the calculations here, you're again going to get 9/4. And then S4. That would be the integral from 5 pi over 3 to 2 pi, and we would have sine x minus sine of 2x dx, and if you go through all the calculations here, you'd get 1/4. So those repeated and closed regions, the area of the regions are either 9/4 or 1/4, depending on which region we're talking about. Determine the area bounded by x equals negative 1/2 y plus 1 and x equals 1/2 y square. Oh, hold on a second. These aren't in terms of, these don't have y in terms of x, they have x in terms of y. So what? We can handle it. Let's draw it. X equals negative 1/2 y plus 1. Hey, this is still a line. If we can find 2 points on the line, we can draw the line. If I let y equals 0, then I'd have right-hand side would be 0 plus 1. Then x would be 1. If I let x equals 0, then I'd have 0 equals negative 1/2 y plus 1. I subtract 1. Negative 1 equals negative 1/2 y. And y would equal 2. It's still a line. Now, x equals 1/2 y squared. You should have studied this in a pre-calculus course. This is a parabola opening right. Not up or down, because the y is being squared. Has a vertex at 0, 0. And then we could substitute some points if we wanted to get some more detail. But I think that's enough to give us a pretty good visual. All right, so let's draw it. I've got a line passing through 1, 0 and 0, 2. All right, so I can draw that. There's my line, and I have a parabola that is opening right. And I mean, if I wanted to, I could, find some other points. But roughly, I think it's going to do this. It appears to intersect. So, I mean, there's the region, right? I've got this region. But if I think about it, I don't really want to draw my rectangles up and down. I want to draw my rectangles left and right. I want to draw, here's a representative rectangle right there. And so I don't want to think dx, I want to think dy. I want to write my integral with respect to y, which means I'm going to need to find the points of intersection where it intersects in terms of y. So let me solve the system of equations. Negative 1/2 y plus 1 equals 1/2 y squared. Oh, let's kill those fractions. I'm going to multiply everything by 2. Negative y plus 2 is equal to y squared. 0 equals y squared plus y minus 2. Let's see, that factors as y plus 2 by y minus 1. Y equals negative 2. Y equals 1. Y equals negative 2. All right, so my lower boundary is y equals negative 2. My upper boundary is y equals 1. Now, my upper function is the rightmost function, right? If I'm integrating with respect to y, my upper function is the rightmost. My lower function is the leftmost. So if I'm going to write this integral for s, it would be from negative 2 to 1. The rightmost function would be the line. Negative 1/2 y plus 1. The leftmost function would be the parabola, 1/2 y squared. And I'm integrating with respect to y. You go through all the calculations. Look, it's the same techniques. You're just integrating with respect to y instead of x. Okay, it's nothing different. And you go through all this, and that area is 2.25. So if we are given functions in terms of y, you may want to write your integral in terms of y as well. You just have to think, okay, instead of thinking left to right, I'm thinking bottom to top on my interval. And instead of thinking upper function minus lower function, I'm thinking rightmost minus leftmost. Use calculus to determine the area of the triangle formed by the points 0, 0, 2, 5, and 5, 2. All right, let's draw it. Zero, 0. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 5. There's a point up there. 5, 2. There's a point right here. There's my triangle. Use calculus to determine the area of the triangle. Now, you may have seen an approach in pre-calculus using matrices to find this area. And even in algebra, you might have seen a method, or maybe in trigonometry, you might have seen a method for finding this area using what's called Heron's or Hera's theorem. But we're going to use calculus. All right, so using calculus, here's what I'm going to do. I'm going to break this up. I'm going to break this one triangle up into two regions, and I'm going to carefully choose the regions. So here's what I'm going to do. I'm going to break it up like this. I'm going to call this region S1. I'm going to call this region S2. And so then the area is just going to be the sum of those two regions. Well, if I'm going to find the area of that S1, I need to know what the upper function and lower function is. And same for S2. All right, so let me give these lines some names. I'm going to call this L1, I'm going to call this L2, and I'm going to call this L3. Line 1, line 2, line 3. Line 1's easy. It passes through the origin, and it has slope. It's going from 0, 0 to 2, 5. The slope is 5 over 2. So line 1 is y equals 5 halves x. Line 2, that's passing through 2, 5, and 5, 2. The slope is -1, and it passes through the point 2, 5. So line 2 is, we can write it as y minus 5 is -1 by x minus 2. And if we put that in slope-intercept form, that's y equals -x plus 7. Line 3 passes through the origin, and it has slope 2/5. So y equals 2/5 x. All right. S1. So then the total area S is S1 plus S2. S1. S1, I'd be integrating from 0 to 2, and the upper function is line 1. So the upper function is 5 halves x, minus the lower function is L3, so that's 2/5 x. And with respect to x. S2 would be from 2 to 5, the integral would be 2 to 5, and I would have the upper function is L2, so -x plus 7, and the lower function is again 2/5 x. And you can calculate these integrals. The first integral ends up being 4.2, and the second integral ends up being 6.3. And so then the total area is 10.5. All right, that concludes this section on how to find the area between curves.